housekeeping issues that I need to tell you. So Mike wants you to and encourages you to participate and ask questions. He's going to talk for about 1 hour and 15 minutes in total, and he can take questions as he goes. But also at the end, I think he definitely prefers to be interrupted when there's anything. And a little bit about him. So Mike is a professor of economics at Stanford GSB, Graduate School of Business. And his work combines great technical depth with a lot of really genuine creativity in modeling and addressing new real life problems. So I was privileged enough to see some of this firsthand. And his ability to distill and communicate the essential in plain English and easy accessible terms make essentially even his most technical papers widely accessible and easy to read. So when I say that, he had contributions across a range of fields, from auction theory to matching markets to information aggregation, industrial organization, financial economics. And all of them were very good. And in fact, several of his papers went on to be selected as best papers across time by various editorial boards of journals or computer science conferences. So that's a testimony to the quality of the work that he's been doing. So I guess without further ado, hang on to your seats and buckle up your seatbelts, as Mike is going to tell us today about carpooling and the economics of self-driving cars.
All right, thanks a lot for such a generous introduction. I'll try to live up to it. And, welcome everyone. It's good to see so many people, a little bit intimidating. And yeah, as you can see, the date on the slides is, it's the first time I'm doing this where my talk spans 2 different days, right? It's May 12th here, May 13th over where you are, but, we'll trying to manage. All right, so this is joined with Michael Schwartz, who some of you may know. He is now at Microsoft. And the title, as Alex already said, is Carpooling and the Economics of Self-Driving Cars. So the motivation for this paper came from this problem that, amazingly enough, does not exist right now, right? So this problem existed up until 2 months ago. It was prevalent worldwide. Cities everywhere in the world look like this. I know where this picture is taken, but people who are not from this country usually have a hard time figuring out where it is. It could be pretty much anywhere in the world. And this is a testament that, this problem of traffic congestion, is, well, at least was universal. And, as soon as the world reopens, I'm pretty sure we're going to be back to dealing with this. And it's a problem that we've had for decades. I'm going to talk about a paper by Vikre that's now, exactly 50 years old, actually 51, just turned 51. He was thinking about this. He tried to solve it. He failed. Everyone else failed. And it's a massive issue, right? You can quantify it in any way you want, in terms of time wasted, in terms of energy wasted, pollution. I mean, it's traffic congestion and time lost and everything else lost is enormous, especially when you aggregate it worldwide. And you can talk about the stress it imposes on others. It even has things like implications for gender inequality, which is kind of surprising, but it turns out there are some very good papers that document that women are more sensitive than men to commuting time, especially when they have children, and so they're more likely to take lower paying jobs that are closer to home. So, huge issue with a lot of different implications. So what makes us optimistic, and sort of the reason why we decided to write this paper, is we think that now is the time when finally this problem may be solved. Doesn't mean that it will be solved, right? And as you'll see, there are some things that we need to fall in place, but it sounds like there is a decent chance that we'll be able to solve it. And there are 3 technologies, and I'll talk a little bit more about all of them. One is self-driving cars, which is the sexy thing as the title, a little bit of a clickbait. The more we thought about this, the more we realized the paper is really not about self-driving cars, but they would help. So I'll talk about this, and it's kind of everyone is talking about this. But there are 2 other things that we think are actually at least as important and maybe more important. and they are a lot less futuristic, right? So the self-driving cars, who knows when we'll have them. It's one of those things that's always 18 months away, right? And it's been like that for the past 5 years. So it's hard to know. The other two, I mean, we're getting there. The other two, where we have real progress, they're happening, but I'm still talking about them in future tense, and I'll explain why. So one of them is frictionless time-dependent tolls, and the other one is convenient and efficient carpooling. Okay. And so the questions we ask in our paper is, what will a market powered by these technologies look like, right? What will the world look like? And then the more practical question, how should it be designed and organized, right? So suppose these technologies do materialize. What should the government do? What should private firms do? Should you have kind of Singapore just telling everyone, up to the minute where they're allowed to go, or are there more flexible solutions? Or should it be just completely market driven, privatize all the roads and let the market figure out what to do? So we'll have at least an answer for what we think is viable and also technological, also feasible kind of in terms of modeling, right? So one of our goals is going to be to define a model that's not just kind of a theoretical construct, but something that's practical, something that can be taken to data and actually implemented. So I'll talk about that. So now before I go there, before I get to the math, is going to be the second half of the talk. I'm going to spend more time than usual on sort of hand waving and motivating why we're looking at the model exactly as it is, why the components are there. And the first step is to explain to you what we mean by these technologies, why we're talking about them in future tense. And then the next thing I'm going to explain is why we think it's important to look at them together rather than separate. Okay, so self-driving cars, it's obvious why I'm talking about them in future tense. We don't have them yet. Who knows when we will have them? So I'm going to skip that. So with that, let's talk about tolls. So why am I talking about tolls as future tense? I mean, tolls are very old. We've had paid roads for centuries, maybe even millennia. And my claim is, as of right now, we actually don't have flexible time-dependent tolls anywhere in the world. And here is roughly why, and here is what's changing. So this is a very current picture from the Bay Bridge and here in the Bay Area, San Francisco Bay Area. So San Francisco is on the other side of that bridge. I don't know if you can see it on your screens. It's there in the back. But what you see, on the front of you, in the foreground of the photo, is the toll collection technology, like as of 2020 in Silicon Valley. And it's similar in most places worldwide, right? So to collect tolls from passing cars, cars have some transmitters in them, and then they have to go through this, gantries that, you make the road much wider, right? This highway, outside of the toll collection zones, you can see sort of in the opposite direction is much narrower. So it basically costs, tens or maybe hundreds of millions of dollars, depending on the surrounding area, to build and maintain one of those things, right? So just the technology of collecting tolls, the process of that is super expensive. And so, for example, even on this bridge, where it looks like we do have tolls, actually in the opposite direction, we don't, right? So if we've got some very enlightened transportation authority in the Bay Area, because what we want to have very carefully done, super intelligent, time-sensitive tolls, they can do it in one direction, but they cannot do it in the other direction, right? Because, we understand why the original goal of this tolls was not to regulate traffic, but rather just to collect revenue in order to pay for the infrastructure. And if your goal is revenue, then of course it's enough to collect twice the amount in one direction instead of collecting it in the opposite direction. And now once you go to the smaller roads, obviously doing this stuff like that is just not feasible, right? So there's just a very basic physical cost of tolls. Now what's happening right now, and so it's going to happen in the near future. Interesting. All right. Is tolls are moving to this other technology, which actually already exists. So, for example, trucks in Europe use this technology to pay for the damage they incur on the road, and Singapore is starting to deploy it on all the roads. And initially, the way they're doing it is they're not going to charge. The formula for tolls is not going to be any different from the way it is right now. They're just changing the technology. But of course, once you change the technology, the tolling opportunities will change dramatically. So what do I mean by this? So this new technology is a combination of satellite-based tracking, right? That's what's shown here in the picture. And, in some location where, satellites are not necessarily very well functioning, tunnels or other stuff like that, you can just put cameras, right? And so this combination of cameras at intersection, with license plate readers and satellite tracking suddenly allows you to do the following. Once you pay the fixed cost of implementing this technology, then the marginal cost of including additional segments of roads in it is basically negligible, right? Instead of the old technology where each segment that you want to price, you have to pay this, tens of hundreds of millions of dollars and slow things down. Here, suddenly you have the ability to really charge tolls for, every little intersection. It can be time varying. There are obviously questions of how do you communicate prices to the drivers, how do you sell them over time? You do have, prepay, et cetera, but these are all kind of other types of questions. They're all questions within this framework where suddenly it is feasible to charge really intricate, time-dependent and tolls that also don't slow anyone down. Okay, so this is coming, and obviously it's going to be very important for what I'm going to talk about next. All right, so this is tolls. The next thing I'm going to talk about, let me try it again. All right, is maybe even more surprising that I'm talking about this as future technology, and that's carpooling, right? So carpooling is probably even older than, surely older than toll roads, right? Like the first time two humans sat on a single animal, right? That's carpooling. And, how can you possibly improve the technology there? And to be more careful, to be more precise, is what we mean in this paper is not carpooling itself, although in principle you could imagine some improvements there and how the cars are designed. But what we have in mind is the technology for finding carpooling partners, matching them, ensuring that they're of high quality, et cetera, right? And if you think about this, right now, carpooling is actually very inconvenient, right? So it's true that, if you have a very regular commute and you have someone who lives nearby, you could find a carpooling buddy. But even then, you lose a lot of flexibility, right? Suddenly, if it's Wednesday, you're supposed to travel together carpooling, and you remember that you wanted to, pick up milk or visit friends, or someone calls you to go to, a restaurant near your work on a short notice, suddenly you lost all the flexibility, right? And that's kind of the best case scenario where you do have a regular carpooling partner. And empirically, despite all the efforts by authorities over the past, who knows how many years, probably going back to World War II, like the government initiatives failed, right? If you look at the number of people who are actually carpooling, right, on the road on kind of any given morning, is going to be in single-digit percentage terms. But that's actually a wildly optimistic number, because of that single-digit number, the vast majority are kind of family members traveling together, right? So it's not like they're carpooling in order to minimize traffic. They will be together anyway. So people who are genuinely carpooling, two strangers who could travel separately but are choosing to drive together, is just absolutely minimal. Now, what's changing now is there are all kinds of apps that are trying to, cell phone apps that are trying to solve this problem, right? And of course, the beautiful thing about cell phones, the technological thing about cell phones, is that they have your location, they track your location, they know where you are. They also have your history, right? They see that if you have a very regular travel pattern, they can predict that with a high probability you will continue having the same travel pattern in the future. So the potential for reducing friction in matching carpooling partners is there. So there is a lot of potential to reduce that. So let me just give you 3 examples. There are more, and none of them has quite nailed it yet. And I'll actually tell you why I think that's the case. Part of that goes back to the tolls. So, hold on to that observation, but they're trying. So here are the approaches they're trying. The first is there is Waze Carpool, right? So many of you probably know Waze, and you probably know it as a kind of real-time navigation app that that has user-generated content. It knows where there are slowdowns. It knows where there are traffic stops and all the other things. And people use it to navigate. Now, because it has so much data about who is going where and when, they figured it would be relatively easy for them to build a carpooling platform on top of it, right? They already have a huge user base, so they're basically trying to leverage their huge market share in navigation apps into a carpooling app. So that's one approach that they're trying. In some countries, it's actually, so Waze it wasn't originally an Israeli company. Now they're owned by Google, but most of the development is still in Israel. And my understanding is that they are actually fairly popular in Israel as a carpooling platform. Okay, so the second, someone raised their hand. I don't know what to do about that. Leslie.
So just a quick question. You mentioned quality of the match. Should I always be thinking of this in terms of just minimizing the time spent traveling to a destination, sort of not going out of your way? Or are there other things that I should be thinking about in terms of being with people like me, or something to do with the flexibility and the ability to cancel? What's the framework?
Yeah, so in our paper, it's going to be completely abstract, right? We'll just say, there is some utility V sub M, there is your carpooling partner, and then you can build in whatever you want. So in practice, I think, obviously the time of detour is kind of super important, right? That's probably, the most important thing in terms of the overall percentage, but other things probably matter too, right? You probably do, if it's someone who you can imagine, talking to, or you would be interested in talking to, that's good. If it's someone who is reliable, right? This platform, in principle, can have data on, if they promise they're going to show up at 8:15, how often do they actually show up at 8:15? Is their car smelly? Do they play obnoxious music? Do they drive? Are they a safe driver? So all of these things can, in principle, be included. And if you see, I don't know if you can see this on the Waze app, they actually have those star ratings for the drivers. So there is some kind of reputation system that you can build in. Okay, so it's a combination of those. And it actually brings us to the second app I want to mention. It's actually the third one on the screen. It's Scoop. So they kind of ask exactly the same question, and they ask who would be a good carpooling partner for a randomly chosen person, and their answer is, it's probably their coworkers, right? So they say, look, if I know that I work at Stanford and Joe works at Stanford, first of all, it increases the probability relative to just randomly drawn people that our ideal arrival time is similar. Also, our geographical location where we want to travel is similar, right? So that's already very good, right? It makes it easier to find a good match. Plus, we may actually enjoy traveling together, talk about work. So that's there's this other component of the match that could be advantageous, right? So their approach, the way Scoop is approaching this, is to start with employers, with large employers, and then go to a large employer and say, okay, let us start here. We will help you match, and we will have you help your employees find good carpooling partners, and it's going to be good for everyone. Okay, so that's their plan. Very different from Waze, but again, as I said, all these companies are trying different approaches, and it's hard to know which one will work, but some of them will. Now the third one is yet another different approach. And that's BlaBlaCar, and what they're doing, and those of you who are from Europe are maybe familiar with this company. So their starting point was carpooling over large distances, right? So if you had students, for example, who are traveling from their college town back to their hometown, for the weekend or for a break, they would be interested in finding carpooling partners just to share the cost of gas, right? So gas or tolls or whatever else, over a long distance, if you're a student, it makes sense to do that. Despite the hassle. So they started as a message board for students doing this stuff, and then they kind of automated it, made it more convenient. And then they say, well, we figured out long distances, so now let us continue improving and shrinking this, distances over which our platform works, making them smaller and smaller, right? And at some point, their hope is they'll shrink it all the way down to the length of a typical, daily commute. Okay. So again, these are all the different approaches to reducing frictions in carpooling, right? So think of this in our model. Also, think of this as a disutility of carpooling, right? They're all working very hard at reducing this disutility. Okay, so these are all individual technologies. So now let me talk about. Let's see. This thing works well, but for some reason, sometimes it gets stuck. All right. So let me talk about the interactions among those three things, right? So I mentioned I'm going to talk about why it's important to look at them together. And in fact, I'm going to talk a lot less about the top part, this kind of sexy self-driving cars part. It's going to be there, but I'm going to go over this very quickly. And if you're interested, you can read the paper. In the paper, we just have like a long list of various reasons why self-driving cars are complementary with carpooling and tolls. I'll just give you a taste of that. What I will spend more time on, which I think is more actually fundamental. Let me see if I can make it thicker. Yeah, right here. It's the complementarity between tolls and carpooling. And in fact, our paper could be written entirely without the self-driving car part. Now, the model I will show you, the mathematical model, actually will rely on self-driving cars. It makes it easier. And the reason for that is when we have self-driving cars, all of the people are symmetric. They're all passengers. They're all riders. We don't need to make a distinction between a driver and a passenger. And that saves us some notation and simplify some of the assumptions. It's easy to adapt our model to carpooling, where you have drivers and passengers. At the end, hopefully I'll have some time, I'll explain to you why, unfortunately, our model, at least the way it is right now, cannot be used for the setting with professional drivers like Ubers and Lyft and other cases. Our model will not be applicable to that, okay? But it will be applicable both to the world with just regular carpooling, where people are not doing it for professional reasons, or for the case with self-driving cars, where there is no driver who needs to be paid. All right, so let me, again, as I said, I'll quickly go through this thing, and then I'll move on to the main kind of complementarity at the bottom. All right. Oh no. Let's see. I'm not quite sure why there is a lag, but gets resolved. All right. So quickly, first, complementarity. Why is autonomous transportation complementary with carpooling? Why is it important to think of them together? And the key reason, the main reason that as we realized, is this one. Let me highlight it. With self-driving cars, carpooling basically blurs the line between solo driving and public transportation. So right now, if you think about how am I going to get to work, you have this very stark binary choice. Either unless you're just walking or biking, either I'm driving, which is kind of in my car, or I'm taking public transportation. There is really sort of nothing in between. And there are some exceptions, of course, here and there, but that's kind of, for most of the world, that's what the commute looks like. And the reason for that is that we have to pay for a human driver, right? And humans are very, very expensive, right? Because if you're a human and another human needs to drive you, it's their time is expensive, and so we end up as a society splitting that cost, along many people, right? So you have to spread the cost across a large number of people, so you end up with large vehicles for public transportation. As a result, they have to make a lot of stops because people live in different places. So you end up with much longer times that it takes them, over regular traffic. And if you could eliminate this cost, right, you could, of the human driver, suddenly you could remove this dividing line and have smaller vehicles, fewer stops, door-to-door transit. Right now, obviously, like what I'm saying, it doesn't apply to every single city in the world, right? So again, Singapore, one of the things they're trying to do is they're trying to make sure that subways are so ubiquitous that from every single point in the city, like it's within walking distance to a subway stop, but there are very few places in the world that are like that, okay? And so, in the paper, we talk about a lot of kind of specific reasons within that framework for why it is so convenient to have those two together. All right, I'm going to skip all those specific bullet points. I have the next page is also full of them. Okay, I'm noticing a lag every time I want to go to the next page. All right, while I'm waiting for this thing to refresh, let me tell you about the complementarity about autonomous transportation and road pricing. Okay, so that's another, Let me see if I can stop sharing and then resume it, and let's see if it works. Share screen, whiteboard, share. No, not whiteboard. Oh no. iPad on AirPlay. All right. Okay, good. We're back. All right. So the complementarity between self-driving cars and road pricing, right? So that seems kind of odd. Why would, what's the connection between self-driving cars and road pricing? The connection is very simple. I'm going to skip logistical reasons. We have them on the paper. They're less interesting for an economics talk. But the basic problem is the equilibrium effect of self-driving cars and road demand during peak hours, right? So when you think about self-driving cars, you say, oh, it's like this wonderful technology. Instead of wasting my time in traffic, right, for half an hour, I can now just, read the newspaper or sleep or play video games or be on a conference call or whatever, right? It's kind of, you're imagining all these amazing opportunities. And of course, from the single agent decision point of view, that's all true, right? So your personal cost of being stuck in traffic goes down. Now, the problem is that everyone else's cost of being stuck in traffic also goes down, which as a result, they are more willing to be stuck in traffic, right? So the things that people do right now to avoid being stuck in traffic, right? Leaving closer, going to work early, going to work later, trying all of the things that they try to do to minimize being stuck in traffic. Now, suddenly, they have a lot less of an incentive to do that. And of course, as a result, overall demand during peak hours goes up. So the trade-off you're facing is right now you're stuck for half an hour, behind the wheel. You will be stuck for an hour or 2 hours, but you can do other things during those 2 hours, and the net effect would, you could easily negate all the benefits from self-driving cars. And we're not the only ones who worry about this. Here's a quote from Elon Musk, right? The reason why I'm picking him is he was kind of on the opposite side. He's a huge champion of self-driving cars, and even he's worried about that, right? So he says a lot of people think that once you make cars autonomous, they'll be able to go faster, and that will alleviate congestion. To some degree, that's true, but the amount of driving that will occur will be much greater with shared autonomy, and actually traffic will get far worse, right? So in that world, regulating traffic through something like road pricing becomes even more valuable, even more important. Okay. All right. So that takes me to the last complementarity, right? The one that I, highlighted at the bottom right here between tolls and carpooling. And this is the most interesting one. And I'm going to spend the most time on this, and then we'll move on to the model. And in fact, Michael and I decided to take this in the paper right now. We just have a short section talking about it. We're going to write a separate full short paper working this out because we think it's very important. And sort of it's a very simple point, but it's kind of totally overlooked. And this is the complementarity between carpooling and road pricing. Okay. And this example is based on this paper by Vickery from 1969, right? Most of you probably don't know this paper. It's actually, you don't know Vickery, it's the same Vickery. The paper actually is it's a short paper, it's a foundational paper in transportation economics, right? He introduced this model of bottleneck traffic congestion, bottleneck model of traffic. It's a very simple model. Turns out it's very powerful. And I'm going to use a kind of very specific special case of this model. And again, you don't need to know Vickery's paper, but if you haven't seen it, I highly recommend you read it. It's really a beautiful paper. Also very influential. So consider a congested road, right? So it's a very simple. In fact, let me try to draw something here, right? So everyone is going from A to B, right? It's a morning commute. And there are twice as many drivers who want to go over this segment over a certain period of time as what the road allows, right? So in the Vickery's model, their ideal arrival times are distributed uniformly from 8 a.m. Till 9 a.m. There is a certain capacity of the road, and we're going to assume he assumes different values. For simplicity, I'm going to assume that the number of people is twice the capacity of the road. And so what ends up happening, and I'm going to draw a picture. Let me see if I can do this. So in Vickery's equilibrium, what's going to happen is the following. So I'm going to have on the x-axis, I'm going to have time. On the y-axis, so this is kind of time, just on the clock. On the y-axis is going to be Q of t, how much time you're going to spend in traffic, depending on depending on what time you pass the bottleneck. And what ends up happening is, there is some peak of traffic congestion in the middle. Traffic builds up to this peak. Traffic gradually goes down. And of course, in the middle, you have this ideal interval from 8 a.m. to 9 a.m., but traffic is spread all the way from a much earlier time to a much later time. And, in the middle, people who are leaving at somewhere in the middle of this interval during the most congested time spend, a large amount of time in traffic. Make sense? Right? And obviously people who are just in the very beginning and just at the very end, don't spend any time. So that's kind of what traffic congestion looks like in Vickers model. Okay, so have this picture in your mind while I'm talking. So now, I'm going to talk about the complementarity between those two technologies. So to talk about this, I'm going to first talk about each of those two technologies separately and then together. And I'm going to argue that together they're much more powerful than each one individually. So first, suppose carpooling becomes very convenient, right? So suppose all these apps I was talking about, they make friction very small, but they're still positive, right? So you're still better off driving solo, but the disutility from carpooling is tiny. You can measure it in just a few minutes per commute. Okay. Well, guess what? This has no effect on Vickers equilibrium, right? It's obviously if everyone carpooled, that would be fantastic. But individually, no one has an incentive to carpool, right? No pair wants to carpool because they don't want to incur the disutility of delta. They want others to carpool, but even if others carpool, they would still prefer to drive separately, right? It's not a coordination problem. It's a basic prisoner's dilemma problem, right? Everyone individually prefers not to carpool. Okay, so this one just completely, doesn't work. And that's partly why I think like for these apps on their own, it's going to be hard to get off the ground, just because for many people, like even if they're super convenient, you're still better off driving on your own. All right, now let's look at the second one. And this is just straight from Vickers' paper. And this is probably going to be more surprising to a lot of people here. This has definitely surprised me with the first time I realized this and thought about this. So forget about carpooling and think just about road pricing, right? And kind of in your mind, you have this idea that, road pricing by itself is going to solve everything, right? Like, when you price a scarce resource correctly, you get an efficient outcome. Okay, so that's true. The basic, theorems of economics definitely hold true. But here is what's disturbing and possibly explains why we have so few actual congestion pricing schemes across the world. So imagine, as in Vickers' model, the drivers are homogeneous. And trust me, things only get worse when they're heterogeneous, right? So homogeneous in the sense that they all value their time identically, right? So there are no rich people, no poor people. They're all kind of equal. The only difference is their ideal arrival time, okay? And then you go and you compute those ideal tolls, right? How much should you charge at, passing this bottleneck at 8 in the morning, 9 in the morning, etc. Okay? Here is the shocking thing that I didn't realize before. After you implement this change, none of the drivers are better off, right? So what ends up happening, let me go back to this picture that I showed you. Let's see if I can, maybe I was too ambitious with this technology. Maybe it dies if I don't touch it for a while. Let's see. All right, let me stop sharing again and share it back. At least I'm getting better at reconnecting, so that's something. All right. Okay, so we're back to this picture. And here is the thing that happens. In the Vickers model, all that happens, the picture remains exactly the same, except that the y-axis gets relabeled, and now these are dollars. Okay? And once you think about this, it's not surprising, right? Because in the original model, people were choosing their arrival times and departure times and in equilibrium. They were thinking, I could go a little bit later, I could go a little bit earlier, and the whole system equilibrated here, right? So all of the drivers are making optimal decisions when to arrive, when to depart. Now, the throughput of the road is not changing. They still have to go, they still have to be allocated in terms of their arrival times from this earliest time until this latest time. So in order to equilibrate things and have them, depart in a regular manner, so as not to create these bottlenecks, these traffic jams, the tolls have to give them the same incentives as what the waiting in line was giving them before. Okay, because otherwise, you wouldn't be able to pass, the same number of people for the same time. And so, again, you can check the math and Vickery, but basically what ends up happening is every single driver, like this driver right here, arrives at work at exactly the same time as before and simply pays in dollars what he or she used to pay in time. Okay, so I mean, obviously things are more efficient because instead of waiting in line, now the government collects the revenue, but you end up sort of unintentionally marrying, conflating this sort of technocratic solution of trying to make sure there's no traffic congestion with massive redistribution. Right now, you can say, well, maybe we can redistribute things back to people in some way. Now, of course, you can't redistribute it just to the drivers without affecting the incentive, right? So in principle, if you have a really enlightened government, and there are a few countries, like a small number of countries like that, I think Norway managed to do it, you can find a way to do this redistribution when you have less trust in the government or less well-functioning government or corrupt government or incompetent government. Good luck doing this redistribution to actually make the drivers better off. And so drivers can intuitively feel that, and they when they see what kind of tolls would be needed, they realize that they're not going to be better off, so there's a lot of opposition. And of course, once you have this heterogeneity, things get even worse politically, because now you have rich people who are going to be able to drive, and then poor people just get completely priced out. I mean, they're just unambiguously worse off. Okay, and this is it's actually something that I'm now thinking more about. This, like in a lot of kind of economics, we have this basic view that all you have to do is just price externalities, and the world is going to be beautiful. And like I'm now realizing, well, there's actually just kind of massive, like the people who are getting priced are actually quite likely to be worse off. Okay.
So Mike,
yeah,
that's all true, but that's for homogeneous drivers, right? Those statements do not necessarily hold for heterogeneous ones, right?
Yes, absolutely. So for heterogeneous, they're not going to hold, so things get more complicated. But then for the poorer ones in the heterogeneous in that pool, things just get unambiguously worse. Right. So think of this as a benchmark, and then if some of the people, I mean, obviously, I personally would love to have toll roads, right? Because I'm in the upper half of the income distribution. I would love that, but if I was in the other half of the distribution, I would not be so happy, right? And that's typically what you see in the political opposition. Okay, so that's sort of the first kind of interesting economic insight. And Vickery actually tries. He's actually kind of uncomfortable about that too. I mean, he tries to spin it slightly differently. He's like, oh look, the government can actually raise revenue in this wonderful way without distorting incentives, but it's still politically quite tough. So now we get to the last bullet point, which I'm really excited about, and that we decided to write a separate paper on, and that is what happens when you have both of these things together, right? So suppose these apps are successful, or they work well, and delta is small, and we're allowed to set tolls intelligently, right? So now what we can do, we can fully relieve congestion, right? All riders arrive at their most preferred time, and they can now be made better off than before. So what do? We just charge a toll equal to 2 delta, right? And if you charge a toll equal to 2 delta, so now everyone has an incentive to carpool, right? Because you're better off carpooling and paying just delta rather than paying 2 delta out of pocket. I mean, here it's you're indifferent. You can add a tiny epsilon here and then make incentives strict. Right, and what you end up doing is you end up doubling the capacity of the road, right? So this is the magical part about these two technologies together, right? Convenient carpooling and tolls allow you to, well, in principle, if you take it to the logical extreme, well, not the logical extreme, if you take it kind of a little bit further and say each car can have 4 people in it, you can quadruple the capacity of the road, but that may be kind of too far out, with a fairly realistic assumption where you have at least one potential partner who is a good carpooling buddy for you. You can literally double the capacity of the road without building anything. And if you go back to this picture that I showed, there are 2 things that are nice about this. One is, as I said, the drivers are actually better off, right? You're not just shifting their waiting time as don't give that money to someone else. They're better off even if the government just burns all the revenue, right? Which is kind of really nice and really powerful. And the second thing is, if I now look at the overall pattern of traffic, all the traffic is now concentrated between 8 a.m. and 9 a.m., right? So all of this disutility from arriving at work too early or too late, right? Which is also a real disutility, right? When people try to adjust their arrival or departure time, that stuff is gone, right? These people, because of this increased road capacity, are now able to travel during the times they prefer. Okay, obviously this is a very kind of bare bones and stylized example, but it sort of shows you the power of these 2 technologies together. Okay.
So,
all right. Now is a good time to ask questions. So my next slide is going to be main model and results, and now is a very good time to ask questions about my 40-minute motivation.
Just as a very high level, what would be then the difference between the carpooling in the last bullet on your slide and the Lexus lanes?
So it depends on what you mean by Lexus lanes.
So by Lexus lane, I mean, imagine I have a highway. It has 4 lanes, and out of those 4 lanes, I'm going to monitor the traffic on one, and I'm going to give priority to cars that have more people in the car than just one person on that lane. So essentially, I'm going to rule out single drivers from using that lane. So that lane is going to basically be faster, and that lane is going to work better. And of course, I can use prices in combination with this. And essentially, it is as if I increase the true output by exploiting that.
Yeah, excellent question. So actually in California we call them HOV lane, high occupancy vehicles lane, or carpool lane. Okay, and yeah, so that's the solution that the government tried to do for many years. Okay, and that empirically doesn't help. Okay, so here, may help kind of a little bit sometimes, but overall, the Bay Area has those, and it's just as congested as it was before. So there are a couple of problems with carpool lanes that I think explain this empirical failure. One is they only apply to kind of some subsegments, right? So if you live right next to a highway with a carpool lane, and your work is right next to that highway, and the entire duration has this carpool lane, if you really have it, most of the time you also waste a lot of time getting to this carpool lane, then leaving the carpool lane, and so things are not nearly as attractive. And Leslie, I see your hand. I'll ask you in just in a moment. But the second thing that's kind of more economically interesting is they actually give you incentives that are not so great. And here's what I mean. So I actually use those carpool lanes quite a bit when I take my kids to school. Now, that's completely the opposite of how they're intended to be used, because I would be taking my kids to school anyway. It's not like this carpool lane gave me an incentive to carpool with my kids, right? So I'm traveling there completely sort of like for other reasons. And in fact, every time you have more than one person in the car, it could be family traveling together, or people are co-workers who are, let's say like 2 electricians traveling somewhere or something else. Suddenly they no longer have an incentive to try to pick their arrival or departure time, right? So they just go and congest this carpool lane, even though if I gave them a little bit of a push with incentives, they would choose a different time. So it's a crude solution that, let's put it this way, it was worth trying. Empirically, it just didn't work. Okay, lesson.
So I guess I have 2. One's more of a half statement question, and the other's a question. it seems to me that part of the issue is that when we were talking about carpooling before the technology, it was something that you needed to schedule way ahead of time because you needed to figure out which coworkers were going with you, and so there was
That's
a
right.
big sort of upfront scheduling issue. Now with the technology, you're able to do it much more easily with random strangers, which means that you can also then respond really quickly to the prices changing dynamically. Because before you could have prices changing really fast, but if your mode of response, which was carpooling, changed really slowly, it had to do with that relative delay that your response wasn't able to move as quickly as your price signals say did. Is that part of how I should be thinking about what you're saying?
I would need to think about this particular dimension. I think it's you can think of this time of response. I prefer to just think about this as an abstract disutility from carpooling, right? All of this inability to respond quickly. Like I would just, so in my model that I'm going to show you, there is not going to be any uncertainty.
Okay.
Right. So think of this as more of a just regular congestion, right? So in many cases, there is definitely some unexpected congestion, but I was thinking more about just predictable congestion. I think it's more about responding quickly to changing life circumstances, right? So I suddenly realize I forgot something. I don't want to carpool with you anymore, but I lose this flexibility. So I think that's kind of the first order thing. But again, you can. I think having carpooling technology be much more flexible and quick and seamless just has a whole bunch of benefits there that I'm not breaking them into pieces in my head, but there is probably some work to be done to do that.
Okay, the other question that I had, and I know I keep harping always on distributional stuff, is that when I think of carpooling and the congestion, there is always this fear with congestion that it's going to be penalizing the poor. It's this whole pricing poor off the road for the convenience of the wealthy. And I think that if carpooling has a much more sparse network in low-income areas, then when you start talking about how these two are moving well together, they might be moving much better together in a wealthier area than in an area where it might not be quite as easy to match because you might not have as many matches available. So I was wondering, have you thought a bit about sort of the network density and how that might interact with then concerns that people have about congestion prices hurting the poor?
Yeah, so great question. We have actually thought about this. And in fact, that was kind of one of our starting observations. And I think, at least our intuition, I don't have any data to support it, but our intuition is I think it's very encouraging because there is some genuine surplus now, right? So poor people can now sort of, they only have to pay half or a third of the time they were spending in traffic. And by the way, it doesn't have to be the case. And in this example, it's really extreme. We have twice as many people who want to go as the capacity. If the access is lower than that, you don't need everyone to carpool. So that's kind of one part of it. But the second part, I actually think, at least where I live in California, I think it's the other way around, that it's the rich people who live in those places where everyone has has an acre and houses are far apart and you can't walk anywhere, and whereas kind of poorer neighborhoods are much more dense. So I actually think that it's going to be that part I don't think is going to be a problem. And if you're thinking about some kind of rural population, right, so you have some poor farmers, that may be true, but then I really don't think they have that much of a traffic congestion problem, right? So I think traffic congestion is mostly for urban and suburban areas, and there you typically have kind of poorer people live in higher density housing. So that would be my intuition.
Okay, that would be it. Actually, I think would be a pretty neat extension, especially when you think about then the public transit network and how much that is actually an alternative to carpooling. Because when you mention the thing of like private car versus public transit, that sort of spectrum by which you can just switch between the two is very different in low income as well.
Yep. All right. Well, so actually that's where I think there is going to be a substantive difference in our predictions for for the world with self-driving cars and without self-driving cars. right? So I think, mathematically our model is going to be, going to treat those identically. Substantively, I think there's going to be more of this discontinuous switch in the world without self-driving cars, whereas in the world with self-driving cars, you'll just have, 6-person vehicles and 8-person vehicles and 12-person vehicles, kind of like you'll just have all these different sizes depending on the density of the neighborhood. All right, so I think this thing got stuck again. I guess it's because of how long of the delay. Let's see if this works. Close, resume sharing. Nope. I know, just as I got to all the math where I really need this. All right, let's try it again. Let's quit everything. At least in a few years, we'll all be pros at this. Let's do it again. Share screen. iPhone, iPad.
For all of us here, it's reassuring that even people from California every now and then have problems with technology.
Yeah, thank you. Maybe I was too ambitious with trying to use I guess if it doesn't work for another couple of minutes, I'll just switch to presenting from my computer. And then I won't be able to mark anything on the slides. Oh, here we go. See, my iPad got afraid. But I'll drop it. All right, so after all this extended motivation, let's get to the math. So main model and result. And again, the goal of the model is actually not just to prove some kind of theoretical possibility result, although we'll do that too. Like, we're really trying to think of this as something practical. And in fact, I'm now working with a grad student. We're trying to quantify some of those things for a large metropolitan area. So in the model, we have a finite set of riders, 1 through m. We have a finite set of road segments, 1 through s. And each road segment identifies both a physical piece of road, think about it, connecting 2 intersections, and a specific time interval. So we have discrete time. Think of this as 5-minute time interval. And so each road segment has an integer capacity QF, right? How many cars can pass through this segment during that time. So now an important element here is going to be a notion of a trip. And now let me make a little bit of a detour from the notation. So I briefly mentioned, the world with carpooling and no road tolls. It's sort of like a prisoner's dilemma in that you want everyone else to carpool, but you individually don't want to. And it's actually a bit more complicated because just mathematically, because we're actually marrying 2 different things, right? There is a coalition formation game here of who gets matched with whom and under what terms. And then there is kind of a game component in addition to that. And in the model with pricing, we're not going to have the game component, but we are going to have a general equilibrium time component. And so our model sort of welds together the matching part, who gets matched to whom and under what terms, and kind of the road pricing component. And they interact, right? Depending on what the road prices are, different coalitions will get formed, right? If prices are very high, the coalitions will be very large, and vice versa. And then depending on what kind of coalitions get formed, that tells you how high you need to set the toll, right? And so the model will kind of resolve both of those together. So now a notion of a trip is an analog of the notion of a matching in the matching literature, right? So if you think about 2-sided matching with wages, you have a firm and a worker and a salary, and that summarizes that relationship, right? Who works for whom and on what terms. So here, we're going to have a notion of a trip. We'll bring in terms later, but this is just a notion of who travels with whom. So a trip is a feasible combination of 1 or more riders, right? Could be a solo rider, could be a combination of 3 riders, and 1 or more road segments, right? So the road segments are the pieces of road that these people need to get where they want to go. So here is a picture. Suppose the road network looks something like this, right? And I'm going to drop the time subscript for just to make it a little bit simpler, here is, one rider. Here is, let's say another rider. Okay, she's sitting here, right? And then a trip could be, right, this segment plus this segment plus this, and then let's say they're both going here. Okay, so this trip involves 1, 2, 3, 4, 5 road segments and two people, 2 riders. Make sense? All right. And of course, there is a large number of possible trips. It's still finite, right? Because everything is finite here, and each trip has a physical cost associated with it, right? Think of this as just wear and tear on the car, like the cost of cleaning the car, whatever else is involved in just physical underlying cost. Like there is no tolls here. All right. So each rider has a valuation for every trip that involves him or her. And notice that this is it's a simple mathematical notation, but in practice, this is going to be there's going to be a lot of logic incorporated into this, because that includes all the utility for different travel times, this utility from having one carpooling partner versus 2, whether you like a particular partner or not, right? Because T is a very rich object, this dm of T can also be quite rich. And then monetary transfers will just enter additively, right? If you have this utility, if you have to pay $3, you just subtract $3, $3 from the V sub M. Okay. For each rider, there is an outside option. It's a trip that involves only that rider and no road segments. Gives M the value of 0 and costs 0. It doesn't mean that it's a utility of 0. Kind of in human terms, it could be that the person chooses just to walk to work or work from home, or bike to work or take public transportation, but basically they're not going to be using any road segments within our framework. Okay, so everyone has an option of doing that, and 0 is just normalization. Okay, so that was we have a notion of a trip, and the next important notion is a notion of an assignment. So an assignment is a set of trips A such that each rider is involved in exactly one trip in A. Right? Just like in matching, you have an individual pair, and then you have a whole matching. Who gets matched to whom? Here is the same thing. So this is, we say, okay, everyone will know which trip they're going on, right? There's this trip and that trip and that trip, and everyone is involved in exactly one trip. So if you're staying home, you're involved in your outside option trip. Right? That's the goal of the outside option, just to make sure that we can talk parsimoniously about trips. An assignment A is feasible if for each road segment, the number of trips in A that include that road segment does not exceed its capacity QS, right? So it's just physically feasible to do that assignment. You're not overloading any link in the network, okay? And then the social surplus of an assignment is just you just add up all the valuations of the riders and subtract all the physical costs, okay? So this is kind of a very utilitarian approach, even more than just basic utilitarian. We also assume everyone has a quasi-linear utility, like we just add up their utility, right? There are questions that are outside of the scope of this paper. What happens if you actually want to put different weights on different people? We're leaving those aside. You have to start with something basic. All right, so now we talk about monetary transfers. So actually, I'm going to first talk about the second bullet point, because that one requires less of an explanation. This is just the tolls imposed by a regulator. And as I'm going to show you, it's not ex ante obvious, but it turns out that it's sufficient to set tolls just on the level of each individual road segment, right? So you don't need to price by the whole route. You don't need to give discounts to carpooling partners. You just charge, a dollar amount for each road segment. So that's that. Now the second part basically answers the following question. So let's go back to this picture that I have right here, right? These are these 2 people, and suppose the sum of all the physical costs and all the tolls for this trip is, $17, right? And so, they're traveling together. There is a question: how should they split $17, right? And that's actually the question that's how we got to this mathematical model. We said, look, how should carpooling partners split the cost? And maybe it should be equal. Each one of them pays $8.5, but that doesn't seem to make sense because one of them is in the car for a longer period of time, so they should probably pay more. But how much more? And I'll give you an answer soon. But for now, I'll just say that answer is going to be encoded by this non-negative vector p that simply specifies how much each rider pays for the trip they get. Okay, so that's going to implicitly encode how this rider split the cost of the trip. And so now we have a notion of an outcome, which is a triple of the physical assignment, the tolls imposed by the regulators, and how the passengers, how the riders split those costs. Make sense? All right. Okay. So now we get to, I showed you the most kind of interesting slide of the motivation. This is kind of the most important slide of the model, right? So I gave you this model, and now the question is, what kind of outcomes do we want, right? How can we be sure that an outcome is good, or, are there any characteristics of, efficient outcomes? So the first two bullet points I have here are just kind of accounting exercises. The first one says, look, you have to make sure that your outcome is feasible, that you're not overloading any segments in the system, right? It's just viable. And the second one says, look, you said that these P's, their role is just to split the cost among the riders. So we're going to there are many ways to formalize this. Turns out that a simple way to do it is to call it budget balance. We say that an outcome is budget balance if the sum of the prices paid by the riders in the system is greater than or equal to the sum of the total physical cost for those trips plus all the tolls on the roads that that are involved in those trips. Okay, so all the money collected from the riders is exactly equal to the physical cost and the cost of the toll. All right, so those are kind of more accounting exercises. Now we get to the two key substantive ones. And this is where this kind of marriage or welding of the matching literature and kind of competitive equilibrium literatures takes place. So first we use this notion from matching. We say an outcome is stable if it is not possible to organize a trip T that makes all the riders involved in it strictly better off than they were under APR. Right? So this is, let me first talk about the philosophy of this and then kind of mathematically what it means. The philosophy is you as a regulator or as a planner can't force people to do what you tell them to do, right? You're not a dictator. You can set tolls on the road, and then you can have, there can be a plan for how people can commute together, how they can carpool, but each one of them, so first of all, each one of them is free to drive solo, right? You have all the solo options. If you don't like this proposed outcome, you're not forced to take it. And also, if you don't like a particular partnership that you're put in, you're also free to rematch. Okay, or you can think of this as a free entry, right? If you have Uber coordinating all these partnerships, a list can come in and say, look, Uber is not doing it right. You three can be better off traveling together and ignoring that proposed outcome APR. Now, what does it mean you can be better off? Well, it means that there is a trip T, right? That's not the one that was proposed. Actually, it's great that it could be just under different terms. There is a trip T such that all of us together who are involved in this trip can take this trip and find a way to split the associated costs, the tolls and the physical costs, in a way that makes us all strictly better off than we were before. Okay? And then we say if such a trip exists, that's a block of the proposed outcome, and this outcome is not stable. The outcome is stable if such blocking trips do not exist. Make sense?
Mike, can I ask something?
Yes.
So this, so obviously, the quasi-linearity here allows you to make transfers between drivers, right? So that's why the strict requirement here is not to
That's right.
the fact that you want everyone to be better off is not that strict.
It makes absolutely, yeah. So it's completely, because everything is continuous here, I could just say, at least one has to be better off and everyone else has to be as well off, and that's exactly the same.
But on the other hand, that assumes that everyone knows everyone else's valuations and so on and so forth.
Well, so that's sort of a standard kind of assumption, again, in matching, it's not necessarily everyone knows everything. It's more that, you know, if there is a way to organize those trips, they'll find that way, right? It's sort of like, think about it this way. If you have an outcome that's not necessarily stable,
Mm-hmm.
I mean, it can persist for a while, but it sort of leaves the door open to, you know, others to discover these unstable outcomes.
Okay.
Right. So it's the same motivation as sort of stability in two-sided matching. Okay.
But in your
all right. Yeah. Go ahead.
But in your model, the valuations, you know, drivers are heterogeneous, and those valuations are private.
So those valuations are private, but if it's a large market, it's not necessarily that hard to, right? In a large market, you can just ask people for their valuation. Now there's a question of how you do it, but it's not impossible.
Yeah.
And they don't really have much of an incentive to lie to you.
Okay, thanks.
Yep. Okay. So this is from matching. Now let me give you an outcome that's feasible, budget balanced, and stable, but not very good. It's the following: an outcome A, everyone stays home, so everyone takes an outside option. Everyone pays 0, so PA is just everyone stays home. P is a vector of zeros, and tolls are, you know, $1 billion on every single segment. Okay, so this is a feasible outcome. It's budget balanced, right? People spend 0, they pay 0, and it's stable, right? So no one can do anything better than this, because anything else would involve paying just way more than their utility. Okay. Now clearly that's a crazy outcome, right? Because we just dramatically overpriced everything, and people stay home, and that's like, no one wants that. And this is where we need this competitive equilibrium logic. And it turns out that all we need is a very simple condition. And that's partly why we're so optimistic about our framework as kind of applicable in practice. What we need is, we say that an outcome is market clearing if for every road segment S that has excess capacity in A, the corresponding toll RS is equal to 0, right? Again, so we say that, and you know, I'll first talk just purely about math, and then after I tell you the mathematical result, I'll talk about interpreting it. So again, you're only allowing to charge positive tolls when the demand for the road is exactly equal to the capacity. Okay, and otherwise price has to be 0. Okay. All right, so here is the main result. You know, we have more, but you can probably see this one coming. Theorem: if an outcome APR is feasible, stable, budget balanced, and market clearing, then assignment A has the highest possible social surplus among all feasible outcomes. Okay, so let me very quickly, I have 7 minutes left, so let me very quickly give you the intuition of the proof. It's actually not very complicated. It's not just a standard kind of first welfare theorem. It's a different theorem, right? Here I'm adding up utilities, but inside it actually combines some standard techniques from the matching literature and some standard techniques from competitive equilibrium literature, right? So it's sort of like the components of this proof are not new. You know, the way it marries those two things together is new. So take a feasible, stable, budget balance, and market clearing outcome A, P, A, and RA, right? So we know that it satisfies those 4 properties. We want to prove that it maximizes social welfare. If I add up everyone's utilities, net of cost, you can't do better than that, right? So suppose, you know, Alex shows up and says, no, here is a better arrangement. Like, I'm a dictator. I know how to do things better. You know, this assignment B is going to produce a better social welfare. And notice that for B, I don't need any prices or tolls, right? It's a completely dictatorial outcome. So I said, okay, let's see. So take any trip T in B, right? And so this is T is in B, and all the riders M who are involved in that trip. Okay, so take all of these riders. Now we know that APARA was a stable outcome. So this particular coalition could not benefit from organizing this trip T by themselves, given the prices they were facing in A, right? So that's just stability of A. So what does it mean? It means that when we add up their utilities in T under A, right? So for each one of them, we simply subtract, we would look at their VM of whatever they're assigned to in A, right? T of M under A, and we subtract their payment, right? So that has to exceed what they would get if they formed this trip T together. So that would include their utilities from T, the sum of their utilities, minus the physical cost of T, minus the tolls they would have to pay for all the segments in that trip, right? So that's just, I just spelled out the statement that APARA is a stable outcome, okay? And so that whatever the trip in T and B, the agents involved would not want to form that trip under the conditions of A. All right, so that's step one. So now comes the key step that, you know, make everything work. We're going to add up those equations one across all the trips in assignment B, right? So the trips T we consider they're all from B, okay? So we're going to add all of them up, all right? So what do we get? So we get, right? So now we end up. So the key thing here is when we do that, we end up going through each agent in the universe exactly once, right? Because each of them, just like in A, in B, they're also involved in each kind of in exactly one trip. So we get the sum over all agents of their utilities in A minus the prices they pay in A is greater than or equal than the sum of all the VMs in B minus the sum of all the physical costs and minus the sum of all the tolls paid. Okay, so now that's not quite what we want. So we have the sum of utilities on the left and on the right, right? That goes, you know, that inequality goes in the right direction. But then what we subtract on the left and on the right is not quite the same. So we need to clean things up. We need to take care of those as well. All right. So for that, okay. So the next step is we know that the outcome is by assumption budget balance. So that tells us that when I add up under A all the payments made by the agent, that has to exceed all the costs incurred there, right? And all the costs are the physical costs in A and all the tolls paid for those segments. Okay. So what I'm going to do now, let me flip back. So I have this term P of A here. All right. And that's what I had here. So because I have inequality going in this direction, I can plug in the right-hand side of this inequality, and then equation 2 now gives me this thing right here. So just if you're keeping track, so we already had stability, so now we use budget balance of this. Okay. So the last thing that we didn't use yet is market clearing. So where does it show up? Well, let's see. So this equation that I have in this yellow rectangle, right? So let me switch to red. These red parts are precisely what we need, right? So the red parts by themselves, you know, the first red part is just the sum of everyone's utilities minus the cost, the physical cost under A. The second one is under B, but I have those pesky sums of tolls, right? So the first one is sum of from, you know, over all the segments of the tolls on that segment times, and now I forgot to explain what this K super A is. K A is just, I'm counting how many times that segment is used under A, and on B, I'm counting how many times the segment is used under B. Okay? But here is the key part that completes the proof. Market clearing tells me that every time RA is positive, right? Every time RA is positive, that implies that KA is as high as it can be, right? That's market clearing, right? You're only allowed to charge positive tolls when the road is at capacity. So KB cannot be higher than that. And so this is going to be true for every segment. And so when I add up across the segments, I get this inequality. And so in the end, this term is, because this term is greater than this one, I can remove all of them and the inequality remains valid. Okay. And we're done. Okay. So I have 0 time left. So let me spend that 0 time telling you 2 very quick things. So one very quick thing is there is an issue with existence. This, outcome may not, this outcome satisfying these 4 characteristics may not exist. What we think saves us in practice is that these are very large markets. So in large markets, we can take kind of continuous approximations, and then we can prove that everything is fine. Okay, so we adapt this notion of quasi-assignment, and then our second theorem says there does exist a market clearing quasi-outcome, which is kind of continuous approximation, and it maintains all of the efficiency properties. And then what does it tell us? Why am I so excited about this? What does it tell us about policy? So what it tells us about policy is the following. As long as as the government encourages and that doesn't put blocks and does whatever it can to make carpooling convenient, and allowed, et cetera, without any kind of monetary incentive, without any kind of road-specific incentive, okay? And as long as those apps are progressing, all that the government needs to do is set those tolls are, and they don't need to, but by our results, they don't need to go through the super complicated optimization, knowing everyone's utilities and going through all of the combinatorics. All they have to do is try to set R in such a way that A, there is no excess demand, right? So traffic is free flowing, and B, they're not charging prices anywhere where there is a substantial oversupply of road capacity, right? It doesn't mean, like, I'm not taking my results literally. That, like, if road capacity is 100 of cars and there are only 98 on the road, then that means that the toll should be 0. Now, that would be too extreme, but it does say that there is some basic principle that you only start charging prices when demand approaches capacity, but then those tolls can go as high as you need to clear the market. That will be sufficient to get the efficient outcome. And on that, I'm going to stop. I think that ends the official part of the seminar, but I'm actually happy to just hang out, and if you have questions, I can stay here and answer them for as long as you guys want.
Right. So let me just thank everyone who stayed so far and has to go. It's been a pleasure to have Mike, and hopefully we'll see you again next week. And everyone else who want to still stick around, please go ahead and ask Mike questions.
Yeah, thank you. So what do I need to unmute people, or how does this work?
Well, let's do this. Anyone who is interested in asking a question, just unmute yourself and go ahead and ask.
Yeah, exactly. Don't worry about hands. Like, where?
All right. Oh, sorry. Coordination problem. Go ahead.
Roger Dargaville from Monash University. Michael, thanks very much for a great presentation. I was wondering if you've seen the kind of road tolls infrastructure that we have in Australia with the very, very fast readers that you don't have to even slow down for. I'm just one of your opening slides when you showed that congestion on the road. And I lived in France for a while where you actually got to stop and put a card in a reader, and it's really tedious. How much of a difference does it make if you don't have to slow down at all for these tolls? Does that make a difference to these?
Yeah. I mean, it makes a huge difference, right? So I think for any system that could kind of work on a wide scale, and rather than just kind of very crude coordinate pricing, you have to have the one that doesn't slow people down. And fortunately, we now have those, right? So I think the reason why, so in France you have to slow down, and the US you have to slow down, is we installed those things relatively early, right? And then sort of, it kind of works. So it's hard to convince people that, we should switch. Whereas if you have a really well-functioning government, or you did those things relatively late, then you might as well adopt the latest technology. technology that doesn't require people to slow down. I think the good thing is by now, many of the systems like the one in the US, everyone realizes they're really outdated. And so we are actually switching to like everything that's new that's being built doesn't require cars to slow down. Right. So I think like, yeah, ripping out the old infrastructure and replacing it, that may take a while, but at least the new segments that we have, they know, you can actually go through without slowing down.
Great. Thank you.
Okay, Emil.
Yeah. So, this is kind of a question that's a little bit outside the scope of the model, but more thinking about kind of practical implementation. As far as I know, in kind of transportation economics, there's this long-running almost observation that demand for roads seems to increase every time you build a new road. There's kind of this conventional wisdom that in that field people have pointed out probably for decades, that it seems like the solution to traffic is not to increase, in some cases, the capacity of the road. And the motivating example that you showed us, in the Victory context, resolved this problem precisely by increasing capacity. And so I wondered, with this kind of also more general framework, you're also doing that, to what extent is that framework really capturing kind of fundamentally all the demand for roads in the economy, right? Because we're sort of looking at a snapshot of what demand looks like in the real world. But, the reality is if we doubled all roads, much like, doubling the capacity of all cars or something like that, and requiring everyone to carpool, we don't actually know, will that suddenly double everybody's trips that they're taking?
Yeah, so excellent question. That's actually, it's very, very important. That's a little bit of an answer to carpool lanes. I think what you're referring to is, I think it's known as the fundamental law of traffic congestion, something like that. That, whenever you add lanes, traffic just, goes back and roads are still congested. So I think that's exactly kind of the point I was making with self-driving cars. It's a little bit the opposite, but I think it's the same type of issue. Now, the reason why I'm a lot more optimistic about our approach is that you also add road pricing, right? So the reason why you have this fundamental law of traffic congestion is, think about it this way. There is some real cost of using the road, okay? But then the government sets the price at zero, right? And so you have this, demand exceeds the supply, so you end up with rationing, right? You end up with traffic congestion, all these other horrible things. Now, if you set a market clearing price, right, then the reason why you increase the capacity, but you don't kind of increase it further because you're no longer charging the price that's lower than the true kind of underlying cost, right? So the fundamental, and in fact, in this world, there is a very natural equilibrating mechanism. If demand starts going up, you just end up raising prices on the tolls will just start going up.
Right. Thanks.
Yeah. So, and that will combat. And in fact, some of the papers that talk about this fundamental law of traffic congestion, they then conclude by saying, look, the only thing that seems to work at all is tolls. But then tolls are, politically unpopular. So that's sort of that we hope, this thinking about tolls together with carpooling can actually help.
Can I actually ask you a follow-up question on that note?
Mm-hmm.
So I guess it would be interesting then to think in your framework, what additional primitives would you need in terms of like the V functions, the valuations, in order to have some result that sort of says like, under what circumstances would you need a dramatic increase in the price of a particular segment? Because this is the kind of thing that in terms of implementation could get really problematic, right? If it turns out that people's demand for segments is highly correlated in some way, and then in order for market clearing to work in this environment, you need suddenly one segment to be astronomically priced. I just wondered, if the solution is we're combining increased capacity with more efficient pricing, then the question is, under what conditions would that pricing give you sort of some maybe questionable or like politically infeasible?
So that's a fantastic question. I'll give you two answers. So one answer is we don't have any theoretical results about that. And we're actually not working on theoretical results about that. So that I think it's an interesting question. So I encourage you to think about that, right? So I think the question, under what are the conditions under which, what we're doing will result in, for example, Pareto improvement for everyone. I don't have an answer for that. I think it would be hard to do it for just completely general road networks. But if you say, okay, I'm going to restrict attention to, to a line, or a rectangular grid or something like that, like I can easily imagine that you can characterize conditions under which different functions VM. So I think that's a hugely important and very relevant set of questions. Now, the reason why we're not working on this is I decided to do something different, and I think I briefly mentioned that. I'm working with a grad student now on actually estimating the stuff empirically for a particular area, right? So instead of giving the conditions, we decided, let's take a large city and just try to estimate those things using the data from that city, right? And just see, who is better off, who is worse off. So it's sort of, if someone ends up writing a theoretical paper with those characterizations, that would be highly complementary. So that's, but I think that's, your question is exactly right. Like we kind of have this very general framework, and then once you start thinking about specific distributional effects in various subpopulations, I think it's super interesting and important, and it requires both kind of theoretical characterizations, which I think are possible for all kinds of special cases, but also empirical work. Which, the reason why I actually went this way is, I presented this in a few places to some empirical guys and said, look, this model is completely empirically tractable. It's actually like, it's just asking to be estimated. Like, well, it's kind of too complicated, too many moving parts. Like, no, like we deliberately made it simple. And then I realized that, the only way to convince people is just to do empirical work myself. So that's.
All right, thank you.
Yeah.
Can I follow up on that?
I guess that partly answers the question in the chat, which was just wondering if you have also evaluated your model under realistic test cases, and if yes, how did you establish your benchmark? So
wait, I did. How do I see the chat? Why don't I see that? That's weird. Oh, because when I did two windows on Zoom, interesting. I just updated my Zoom to version 5, and they made it better. And part of making it better, it didn't show me the chat. Oh no, there are 5 questions in chat. I feel bad. Okay, iPad to the computer via cable. Good, thank you. Need to go. Sorry, everyone. Thank you. Okay, question from someone. Yeah, just wondering if you have also evaluated realistic test. Yeah. So let me tell you a little bit more about the empirical work we're doing. So we're trying to actually get data on traffic patterns. And we're going, so what our plan is the following, and I'm actually kind of curious about feedback. Our plan is to set it up in a way that you can plug in your assumptions, right? So what we're going to do is, some things we can estimate, right? Like we can estimate populations, we can get data on how many people are traveling from any particular neighborhood to another neighborhood, right? Distances, all of that, we'll just kind of hard code. But then there are some other parameters like the disutility from carpooling that are much harder to estimate, right? We'll get some estimates from the data. We'll do the best we can, but then we will keep them as relatively kind of easy to change parameters, and then we'll circulate the model and the computer model, in some convenient fashion. And then if someone says, oh, you put delta at $2, I think the true delta is $4. Let me see how the results change. Or something else along those lines, you assume that 2 people can carpool, I think 3 people can carpool, right? Stuff like that. And then, they'll be able to press a button and see how the answer changes. So I think, our approach is going to be like that. And then in terms of establishing the benchmark, we, in a similar fashion, we'll try to estimate the current, right now, how much time are people wasting in traffic, and that. I think that's a pretty good benchmark. More questions?
Can I make a follow-up comment on Emil's question and your answer? Sure. So there was a mention of very high correlation on some arbitrary segment, for example. Wouldn't that dictate what technology is being applied on that segment? So this is, for example, if a lot of people want to go from A to B at the same time, you have choices that could be to increase prices dramatically or transportation capacity. So put buses as opposed to cars on the road. No?
Okay, so yeah, good. So there are a couple of, I have several different answers on that. So if there is some road segment that just has really massive demand from A to B, right? Presumably we already have some kind of public transportation there, hopefully. Right? If not, or we have LA where you just have like everything is super congested. Now, if you have, and this is a very optimistic view, right? So once you start having tolls, and once tolls start skyrocketing, that gives a major